I'm hoping now that you kind of have a feel for the overall mitochondria from the preview talk, in the fact that so far what we've done is we've done glycolysis, we pump pyruvate into the matrix. There, it has been oxidized to make acetyl coenzyme A to run the citric acid cycle, which makes mostly NADH. That in turn, those high energy electrons will be dumped into the electron transport chain, these transmembrane complexes in the blue inner mitochondrial membrane. As the electrons fall down the electron transport chain, that falling in energy of the electrons all the way to molecular oxygen is going to drive protons through the membrane. It's going to pump them into the inner membrane space between the inner mitochondrial membrane and the outer mitochondrial membrane. Now you'll have a proton gradient, and literally this is a battery. There's a lot of protons in the inner membrane space, and there's a lot of hydroxyls in the matrix. And literally there's a charge difference across that membrane, and there's a high entropic difference. Things tend to go to low concentration, so the protons tend to be driven across the membrane. But protons are positively charged. They're stuck in the water. There's no way that a charge can get through a membrane. The only openings for them to get through are in the ATP synthase. Oh, you can't see my pointer. That's right, okay. The only thing they can go through is the ATP synthase. That's the only avenue they have to return. And as they are driven through the ATP synthase, then that will force this rotor to turn. Literally, it is a machine, a mechanical device that's going to turn. And now we're going to zoom in and look at the ATP synthase. And again, if you had trouble making sense of the electrons falling, and I really wanted you to try to understand that mechanism. How is it? It's not just, oh yeah, they go down, something goes up. But if you actually can understand a little bit of the mechanism, I think the whole thing makes more sense. If you had trouble with it, get in touch with me. But now let's look at the synthase. We have the proton gradient. The protons are being driven. So we have the intermembrane space where most of the protons are. And on top, we're showing the matrix. And literally, there's an opening into the C subunits shown in yellow that are transmembrane. Now, this is not a learning objective, but if you ever read about these ATP synthases, you'll probably see the nomenclature F1 and F0. When they tried to purify these things, they found that chunks of them were soluble. That's all the stuff that's in the matrix. And that the transmembrane proteins were completely stuck in the membrane, so they separated. The stuff that was lipid soluble, they called F0. The stuff that was water soluble, they called F1. And they named this A, B, and C for the transmembrane lipid soluble parts, and alpha, beta, gamma, and delta, and epsilon for the water soluble parts, because that's how they were able to purify them. Now, that's not how they work, though. In fact, when they work, you should think of the subunits differently. And in particular, the C subunits that are transmembrane, and then the Greek letter ones, the epsilon and delta, form a rotor. And that rotor turns, outlined in green, turns with respect to everything else. So you have the A, B, and then alpha, beta, gamma, delta parts that are all being turned with respect to the rotor. So it is the interaction between the transmembrane A subunit and this highly symmetric 10 subunit, C10 subunits that drives, that the protons drive a rotation of those symmetric C10 subunits. And the gamma rotor that sticks up in between the alpha and beta subunits is asymmetric. And so that means that as the rotor turns, the alpha and beta subunits are being distorted in a cyclic way. So at one time, the alpha subunit is distorted. Then as it turns, the next alpha subunit is distorted. As it turns, the next alpha subunit is distorted. So there's a repeating cycle. And every time this rotates around one time, you've gone through a cycle of 3 identical steps at each of these being one step out of sync with each other. And so in here I'm showing a proton coming in and driving the rotor to turn. Now, what's really interesting about this is this mechanical energy. It's motion, it is a machine. That mechanical energy gets converted into chemical energy as the rotation of the rotor literally drives the formation of ATP from ADP in inorganic phosphate. If we're looking at the C10, the symmetric wheel of the rotor that's in the membrane, and the A subunit is linked to the B subunit, linked to the delta subunit, so that the rotation of the C10 subunit with the epsilon and green gamma subunits, that all rotates with respect to everything else. So the alpha beta wheel is linked to the delta and B wheel, so those are different parts again, as I show here. And now if we zoom in and look at that interface between the A subunit and the symmetric 10C subunits, it's going to look kind of like this. So the A subunit I'm showing in purple, and the C subunit I'm showing in blue. And there's an aspartate residue near the middle of these two alpha helices. And again, there's 10 of these pairs of alpha helices making a wheel. And this is just one of them. And you see how the aspartate is right next to one of the half channels? The whole idea is that one of the half channels is open to the matrix, the other half channel is open to the intermembrane space. So protons move extremely rapidly through water, but they can't get through membranes. But they will come, let's say that the intermembrane space is at the bottom of this figure. At the bottom of the figure. So the protons can come up to this channel. Are they going to be able to get through to the intermembrane? Are they going to be able to, I'm sorry, the bottom will be the intermembrane space. Can the protons get through to the matrix? Can they go down the gradient and get to the matrix here? They can't. But we have a lot of protons. We have so many protons that if you think of the pKa, the proton can stick to the aspartate. And again, this is why I think it's in your interest to check out my office hours tomorrow, where I talk about the charge can't get through the membrane. It can get into a liquid channel and it can bind to the aspartate, and now the aspartate is neutral. So with a so here we're showing, I'm showing two neutral charged aspartates on the purple A subunit, and I have 10 C subunits on the inside. So the negative sign here represents an aspartic acid. So let's say then that the intermembrane space is above. Will there be more protons above or more protons below? If the intermembrane space is above and the matrix is below, where will most of the protons be? Because they've been pumped by the, yes?
In the intermembrane space?
Yeah, so most of the protons are there. So which of the two negative signs here, aspartate residues, which is most likely to grab a proton and become neutral?
The one exposed to the intermembrane space?
Yes. So now, every one of you, I want you to think, which way, looking from the top of it, which way will this rotor turn? And again, this all goes down to the fact that a charge cannot go into a membrane. It cannot be buried in a membrane. Whereas, even a protonated aspartate may not like to be in a membrane, but it is neutral, and it will much more easily go into a membrane than a charged one. So, does someone want to answer which way the thing will turn? Looking from the top. Okay, someone said counterclockwise, and that's correct. Now, I'm hoping everyone sees that, and I don't want to spend a lot of time on it, but think about it a little. You can watch the video, and it's just an idea of, it's so clear how this is working. Now, you see, the protons don't actually give a force. The force is just by the random Brownian motion. Things that are so small bounce around from high to low energy conformations. And if they're protonated, that allows one to move into the membrane. And of course, as it does that, as a proton comes in and moves, the thing can move counterclockwise, as you just said. And then, as it moves counterclockwise, the proton that was in the C10 subunit outside of the A subunit in purple will move in here, and will it tend to come off or stay on the aspartate in the lower half channel? The high proton concentration drove the proton onto the rotor on this side. On this side, with a bunch of hydroxyls, that one proton will tend to come right off to make water. And that's what, and with the Brownian motion, so really what the proton gradient does is it's sort of like a self-winding watch. It allows, you're turning because of Brownian motion, but it decides which direction to go. And again, any questions on that, don't hesitate to ask. The other question I have is,
so Dr. Hansen, you said counterclockwise, but it looks like it's turning clockwise.
ooh, this is clockwise. Yeah. Wow, don't I know the difference?
Okay.
Sorry about that. I was reading one of the answers, and yes, thank you very much. It turns clockwise. And by the way, I was just testing to see who was paying attention, okay? Yeah, so that's the one problem in biochemistry. One thing goes up, drives something down, which drives something up, which drives something down. You just trip up on one of them, and you end up messed up, so I really appreciate that. Yes, that is clockwise for people who don't know the difference.
I just had to look at my watch, that's all.
I really appreciate it. So now my question is, again, in the half channels, it will depend whether they're going into the membrane or coming out of the membrane, the rotation, whether there's a proton there or not. If there is a proton, it'll come off on the inside. It'll come in from the top. So what about the subunits which are in the membrane? Will they be all protonated, all deprotonated, some protonated, some deprotonated? So if we ignore these two blue subunits in front of the purple, what about the rest of the subunits? Will they tend to be protonated or deprotonated? Can a charge exist in a membrane, trapped in a membrane? Let's see. So yes, I'm gonna go here and look at the top view. I think a couple of you got it. So the thing is that proton comes up and sticks on, and now it can rotate into the channel. That proton can't escape, because to escape it has to go through the membrane. As long as it's stuck on the aspartate, it's okay. So it cannot come off until it comes out of the other side. But I just want to say that I'd like to spend more time on that, and I have a couple other videos and all, but I want to go up to here now, and I want to begin looking at a top view of this, the synthase. And here I'm showing the rotor turning. In this case, I'm showing it counterclockwise. You must be looking from the other side of the membrane in this case. But you see how the rotor itself is asymmetric, this gamma subunit. And so actually the beta subunit shown in red has 3 different conformations, and each one of those beta subunits goes through the exact same conformations, each one step out of touch with the other. So one rotation of this, each one of those, all 3 of them will go through all 3 conformational changes in one step. And each step is involved in making ATP. And now I want to look into the beta subunit itself. And I want to look where ADP, inorganic phosphate, and ATP bind. Oh, before I do that, I want to go to the next slide. Can anyone tell me, I hope you watched the coenzyme talk, because it really makes a big deal about this. ATP, here I'm showing a picture of ATP at the bottom. Why are the phosphoester bonds, why are they high in energy? What makes them high energy?
Lack of resonance.
Resonance, yep. Resonance plays a gigantic role. And in addition to the resonance is the negative charges. You have these very tight phosphate groups with 4 negative charges all trapped together. If you nucleophilically attack the terminal phosphate with a water molecule, you can form an intermediate. The phosphate can come off. Now this phosphate that just came off, will it stay there right next to the diphosphate? Will it get closer, or will it move away? Can someone tell me?
It'll move away.
Yeah, these are trapped together in the bond and they're repelling each other. And if you can break the bond, they fly apart. So what does the ATP synthase have to do? Somehow it has to pull them back together. It has to pull those negative charges right on top of each other to do the reverse of that reaction. And that's why it takes energy to do it. But now I want to look here at how the enzyme does it. So the charge is causing these to repel each other, right? So the beta subunit has a large holes on it. In fact, this is a single hole I'm showing in two different settings. The point is that all these positive charges cause the triphosphate to bind. The phosphates are negative, the diphosphate is negative, the triphosphate is negative. So this huge positively charged hole grabs them, okay? Now, if it grabs ADP and inorganic phosphate, will there be any difficulty in getting this diphosphate to nucleophilically attack the phosphorus? In solution, you can't do it because they repel, right? But what if you're in a sea of positive charge? Can you form the bond?
Yes.
Yes. And in fact, it's primarily these negative charges. Also, these positive charges are interfering with the resonance to begin with. They're stabilizing one form over another. And I will tell you that on the beta subunit, that beta subunit, the free energy difference between ATP and ADP and inorganic phosphate is essentially zero, which means you can make ATP for free. Do you like that? You're producing ATP, the most important energetic courier in the cell, and you're making it for free. But wait a minute. How can you make ATP for free? There's a problem, right? It costs energy, right? You had to do the work. You had to push them together. Well, I'll tell you, there's a problem. You know what the problem is? You've made it, but what about these? You've made the ATP now on the synthase, but look at, we have all the negative charges in a pocket with positive charges. Will this ATP be able to diffuse out?
No.
It's profoundly, electrostatically, it's trapped. And I'm like, oh, I need to make ATP. I don't need it stuck on the synthase. I need it in solution where I can run my muscles or work my brain or pump ions. So so the problem I'm trying to figure out, how do you think, can anyone come up with an idea how to get the ATP, the negatively charged ATP, out of the positively charged pocket? If only there was some type of something to push it, say some type of mechanical force that could physically separate these things. Like if I could grab it and pull it out, right? Or reach my hand in there and push it out. Any idea where you do something like that, where that could come from?
Is that the gamma rotor, the uneven gamma rotor?
Yes, that's the exact answer I wanted. Does that make sense? This is how the mechanical energy of the ATP synthase is not informing the chemical bond. The chemical bond is formed completely for free. It's just you can't use it. But when you push, when that rotor turns, it literally pushes the thing out. Now, I just wanted you to have a feel for the logic behind the system. Literally, you're using mechanical energy, push the ATP out. You can rotate again, another ATP and inorganic phosphate bind. They can form the triphosphate for free, rotates again, gets pushed out. I just think it's a really nice story, and it's dependent upon recognizing the nature of the high energy bond in ATP. Now, as pretty as that story is, I don't expect you to take my word for it, okay? You can't trust every scientist. So here's a picture of a crystal structure showing ATP. Oh, do you see that? Did it show up on yours? Do you see the crystal structure?
Yes.
Good, I didn't know if
Yes.
I changed that. Okay, so here is an adenine ring in blue and gray, the sticks. The phosphate group shown in gray in red oxygens, and the phosphates themselves in brown. And here, I guess, is the inorganic phosphate, but it's kind of in this weird state, being held by various metals and all being held together where you can form or break the bond at will with no trouble at all. Just kind of a pretty picture to say, I'm not just making this stuff up. Now, once the ATP is released, or if the inorganic phosphate is free in solution, we have all of this resonance, as you mentioned, so the electrons smear out and are happy. I'm hoping you understood that model, both how the falling of the protons, the falling of the electrons pumps the protons, how the protons drives the rotor, how the rotor frees the ATP, so you've made ATP. And you can, this is not important, but you normally think of an enzyme. You have an enzyme and a substrate, and it makes a product where the change in energy is the chemical bond. But here, the change in chemical bond, there's no change in energy, but getting it from the synthase into solution is where you have that big change in energy. You don't have to be able to interpret that. It's just meant for those of you who like chemistry. And now I want to skip over some slides. You can look at them on your own, but I want to go up. We've really talked about that. The rest I'm kind of summarizing, you know, the number of protons and electrons in these processes. I recommend you look at it to see if it makes sense. But I wanted to talk about a problem in Wisconsin. You know, normally you want to have ATP so you can run from the bear, right? Or so you can pump sodium against potassium, or so your brain can think. But it turns out that in Wisconsin, sometimes we have other problems on our mind, such as freezing to death. And now, I can go back here. Of course, we burn glucose to carbon dioxide and water, just like a fire, but only half of that energy is formed as ATP. The other half makes heat. And so there are times where, yes, you have enough energy, but you need more heat, especially here in my home state of Wisconsin. But there's a problem, and that is if we look at these are the three complexes I talked about, complex 1, 2, and 3, and 4. And all of them constantly are pumping protons. And if you don't understand the pumping of proton, talk to me. We can explain it relatively quickly. But the protons are pumped out. Well, the only way for the protons to get back in is through the synthase. And that means if you're doing oxidative phosphorylation, you're making ATP. Not only is it good that you're making ATP, but you don't have a choice. You have to make ATP. So now I'm out in the sub-zero weather in Wisconsin, and I have too much ATP. There's so much ATP that the synthase can no longer turn. I can't find any ADP and inorganic phosphates to bind in there. But somehow I still need to be doing oxidative phosphorylation to stay alive. So we need some way to let the electrons fall to molecular oxygen without them being linked to phosphorylation. We need to decouple oxidation from phosphorylation to avoid freezing. Does that make sense? Those are the huge things. Okay, so now how do we do that? Well, there's something called the decoupling protein. And what it does is, look what it does. Can anyone, I've drawn a picture of, I'm sorry, the uncoupling protein. You know, but anyways. Can anyone tell me how the uncoupling protein is able to separate oxidation from phosphorylation, to uncouple those? And again, oxidative, phosphorylation, two different processes. How are we uncoupling them?
Didn't they give like another pathway for the protons to go through besides ATP synthase?
Yeah, is that elegant or what? You know, it's just, wow, what a simple solution. And there's a number of things which stimulate the production of the uncoupling protein. And I should point out that when you're freezing to death, that is absolutely takes place. You start producing more uncoupling protein and you can burn sugar. You see, if you're completely topped out on ATP, you cannot run the electron transport chain. You cannot burn the sugar. But if you put a hole in there and the protons can go without going through the synthase, now you can keep burning sugar and you can keep making heat. There's another way you can make heat when you're in the cold and it's really cold, and that is to burn the ATP. Do you know how your body automatically can burn ATP without you even having to run?
Shivering?
Yes, shivering is your way to burn ATP so that you can keep these oxidation reactions happening and keep making heat. But this is much nicer, I think. Shivering is no fun. Anyways, but both those mechanisms are relevant. The uncoupling protein has another name. And did you already listen to Dr. Zawada's talk about heat generation?
Yes.
And so what did he call the uncoupling protein? I don't know if he referred to it, but he talked about a protein that does this. He mentioned a name that it's involved in making heat. Maybe that gives you a clue.
Thermogenin.
Yeah, thermogenin is the uncoupling protein. So, and it's useful to know that because that kind of ties our talks together. I thought he was actually going to talk a little bit about this, but I guess he said, well, figured if I'm doing this, he'll just talk more about its regulation and all that. But this underlies his talk quite a bit. So, okay, we've already answered this question, and we are getting fairly near the end. But I want to point out that you really have two types of fat in your body. You have white fat and you have brown fat. What is the purpose of white fat, most of the fat in your body? What's its general purpose overall? You need it to survive for a year if you don't have food.
Energy storage.
Energy storage. In contrast, brown fat is energy usage, and in particular, it's to keep you warm. Do you think that a baby or an adult will tend to have more brown fat?
Maybe.
Maybe.
Babies have a lot of brown fat because they have small bodies that lose their heat very rapidly, whereas we have big bodies that are, we can take care of ourselves better. Babies have a lot of brown fat, and as you age, the brown fat decreases, but we all have some of it in us. If you want to lose weight, would you rather have brown fat or white fat? White fat stores energy, brown fat tries to burn it.
So you want brown?
Brown fat.
Yeah, brown. I wish I had more brown fat. I'm getting a stomach here with this COVID stuff. Do you know, and what makes brown fat brown? It's very similar to white fat, but it's discolored. It literally looks brown instead of white. Any idea why? What it might have a lot of in it? Right? Yes?
There's mitochondria with iron.
Yeah, there's a lot of mitochondria. They store fat, but they're ready. When you get cold, they're ready to burn it. They need, and literally it's the mitochondria, and it might be the iron component. I have to think about that, but certainly mitochondria tend to look darker than your typical cytosol, and fat itself is kind of whitish. So it's that mass amount of mitochondria. The iron in it might play a role, but that's why it's brown, is because of that role. In this uncoupling protein, this is called a futile cycle. So in other words, normally you do oxidation, the electrons fall through the transport chain in order to power the ATP synthase, and you make ATP. But when you put in the uncoupling protein, when you activate it, then it's called a futile cycle because you're not making ATP, you're just wasting the energy. You pump the protons, they come back to you. You pump the protons, they come back through. A futile cycle is kind of an important word. There are a number of possibilities for futile cycles. And one other question for you now. You know that most of the free radicals in your body are made in mitochondria. That's because, and what is the primary component responsible for formation of free radicals? There's actually one of the coenzymes involved in the electron transport chain actually has a radical. Coenzyme Q is the #1 source, and actually it's very prevalent at complex 1 and complex 3 where most of the free radicals are formed, and they're harmful. Now, do you think there's a free radicals signal or regulate the uncoupling protein? Do you think that a high concentration of free radicals is going to increase the amount of the uncoupling protein, increase the number of channels, or will it downregulate it and decrease it? And to answer the question, you have to think, the problem with free radicals is they form because molecular oxygen bumps. Now, molecular oxygen, if molecular oxygen bumps into ubiquinone, can it form a free radical? Or if it bumps into ubiquinol, can it form a free radical?
Ubiquinol.
Which one again?
known, O-1-O-N-E.
Well, sorry, I'm glad you took a step, but the thing is that is molecular oxygen going to tend to grab an electron or donate an electron to become a free radical? Oh, and by the way, this is
It would donate.
okay. This is in my Why Do We Breathe? It really explains this in detail, and all these answers will be trivially simple for you to answer if you watch that. I do recommend you find the time. If you're listening to it and you get stuck on any part of it, you don't need to memorize it. It's there. And I wouldn't even make many notes, if any. I would listen and say, does this make sense? Does this make sense? And if you get stuck or something doesn't make sense, give me a call. I don't want you spending hours on this. I really hope you'll listen to it. Molecular oxygen is one of the most electronegative atoms in the periodic table. That means it's near the right-hand side. Its outer shell is almost full of electrons. Anytime oxygen forms a bond with carbon or hydrogen, it grabs electrons, it pulls them over their polar bonds. And so molecular oxygen bumping into a coenzyme, if the coenzyme has a free electron, it can grab it. Ubiquinone does not readily give up any electrons. That's the other thing, kind of a way to simplify things. NADH, FADH2, ubiquinol, nol, alcohol, OH, all those have H in them. That's because that hydrogen or hydride ion is reduced, it's electropositive. So if you have an H on the end of a coenzyme name, you can go, that's the high energy form. It's donating it or not. So if molecular oxygen bumps into a coenzyme that's in its high energy form that has electrons to donate, like NADH, FADH2, ubiquinol, it can grab one of those electrons. And mostly from ubiquinol, because ubiquinol goes from ubiquinol to ubiquinol radical to the ubiquinone. In ubiquinone, there are no more electrons that are ready to grab from it. So it's these, if you have a lot of high energy, such as us Americans who eat too much, then molecular oxygen can bump in to those high energy electrons and form a free radical, and then it'll harm you. So anyways, if you have a lot of free radicals, the body interprets that as if you have too many high energy intermediates, too much NADH, too much FADH2, too much ubiquinol, or QH2. And therefore, it wants to produce the uncoupling protein so that you can get rid of the gradient and start letting some of those high energy coenzymes convert to their low energy oxidized form. And we'll talk more about this balance in future talks, but it's real important that we eat too much, we have too much fuel, from it we make too much high energy reduced compounds, and as a result we're subject to free radical damage. And that's really an important part about diet and all that, but we'll come back. If you had trouble with any of this, don't hesitate to give me a call, email me, whatever, and I hope some of you show up for office hours. Are there any questions on any of this?
I have a question, Dr. Hansen. Can you just repeat for, the problem with Wisconsin? So even though we have extra energy like ATP, we still need to run the oxidative part of the oxidative phosphorylation. Why is that again?
Okay. So half of the energy you get from glycolysis, half that energy is released as heat, right? The other half takes the form of ATP. You see the ATP here?
Yeah.
Okay. Now, say that you are freezing to death, and so you're running oxidative phosphorylation as fast as you can, and all you have left in the matrix, that's an excellent question, by the way, I love it. All you have left in the matrix is ATP. There's no ADP left. If ADP is not around, it cannot bind to the synthase, it cannot accept the phosphate, the rotor cannot turn. And what I'm saying is that it isn't just that the protons going through the rotor make ATP, they have to make ATP. The rotor can only turn if inorganic phosphate and ADP bind, form ATP, and then get kicked off. So it's like a clog in the wheel. Does that help a little bit? It's a simple statement, but that's the interesting thing, is that the proton going through the rotor, it can't go through without turning, right? Because they're half channels. The only way the rotor turns is if the proton goes through. And the only thing that allows the rotor to turn is if ADP and inorganic phosphate bind and get converted to ATP. Because otherwise, you can't undergo the conformational changes, because those are involved in ATP versus ADP. It jams up the ATP synthase. And in fact, almost every energetic process I talk about, it isn't just that, wow, you make ATP, wow, you make NADH. It's you have to make it. It's good you make it. And normally I think, oh yeah, I want a bunch of NADH, I want a bunch of FADH2, I want a bunch of ATP energy. But there is such a thing as too much energy, and a lot of Americans suffer from that. Can you ask more about that, if there's any part that didn't quite add up?
No, it adds up. I finally get it. So it has to do with regardless anyway, but then that's why the uncoupling shows up, because you don't want to keep on making the ATP because you have so much, but you still want the proton to get in there as well.
And in fact, if you have a bunch of protons inside and a bunch of ATP, the ATP will drive the synthase and pump the protons out.
Oh, that's crazy.
It'll turn in the opposite direction. Yeah, it's kind of a neat story. But again, I really like that question. That's the exact type of thing. Wait a minute, why is that? It's the fact that they are coupled. It's good that you make energy. Maybe it's bad that you have to make energy, but then again, you want to be able to control whether you make energy or not, and that's why you put in the uncoupling protein. And I hope if anyone else, I think a lot of your colleagues had that exact question. And so it's a real important thing to emphasize, the fact that coupling means that, yes, you make energy, and in addition, you have to make energy. That's what coupling means. It's not just this reaction, but it's almost all these reactions. The electrons cannot fall unless they pump protons. Kind of neat stuff. So again, I hope that I see a few of you tomorrow. I changed my hours to 6. I hope Dr. Pong's directions are going to help you find where those office hours are and the link are. If you can't find them, email me if you're trying to go there. And don't feel constrained to office hours. If you're working on this stuff, you can call me at any time. We probably will spend 5 minutes to answer something that might take you a half hour to figure out. Seriously, you know, that you could save yourself a lot of time. And I've actually had a busy week talking with a lot of your colleagues, and I enjoyed every minute of it. So, but I better let you go. I know you have a talk at 11. Again, please feel free to move on to the next talk. I'm going to stop recording. And if anyone has questions, don't be afraid to ask.
Thank you, Dr. Hansen.